Okay, hello everyone. Welcome to Recitation 5. Today we're going to be talking about Chomsky's normal form and GNFAs. Now, Recitation 4, we did have it on campus, but I made an offline recording of it and it's been uploaded. You can revise it if you ever need to. Whenever we have an on-campus recitation, I'll try to make an offline recording just in case somebody wants to revise that stuff. So last time we talked about pumping lemma, PDAs, CFGs, etc. I would like to solve more in these, especially on PDAs, since it was the last idea we talked about. Maybe we'll do that next Tuesday. For today, we'll focus on these two ideas. So Chomsky normal form and GNFAs. Let's start with Chomsky normal form. So it's a method to transform your grammar in a certain way. So it's a grammar where every production, so every rule is either of the format one variable goes to 2 or the variable simply terminates. So if you remember from last time when we made certain grammars, we had something like s goes to 0, s1, or x maybe goes to 0x and stuff like that. So these aren't really allowed in this case. It's only either you go to 2 variables or you terminate. It's kind of like we're building a binary tree. So like imagine, let's actually use the example that we have. So in the example, S goes to AS or it terminates with A, and A goes to SA or it terminates with B. So it's kind of like this. We start with our S. So usually S is your start variable, but it should be usually specified. So S is my start. It's like I'm replacing it with A and with S. Then this A, I can replace it with S and an A. And this one, I can replace it, and so on. So it feels like we're building a binary tree, and that there's a lot of usefulness for this. Mostly it has to do with how long it takes you to generate your strings. We won't dive too much into that, but there are some interesting things. So eventually, this S can go to A, this goes to B, this goes to A and to B. So we made like the string AB, AB. Okay. So what are the steps to do this? Similar to maybe the pumping lemma or similar how we transformed a DFA, an NFA to a DFA, there are certain steps. And there are these. Step 1, get rid of all epsilon productions, all the epsilon rules. Get rid of all productions where the right-hand side is just one variable. If we have really long productions, make them shorter. And move all the terminals to productions where we only have one terminal. Now I'm going to explain each one of these in detail, so don't worry if you didn't get one of them. But I want to mention first, like there usually is a step even before all of these, where we make our start variable, where we make a new start variable. So say you have your start variable s, we'd make a new start one, so make new start variable, something like maybe s0 that goes to s. So if s is your old start variable, your new one would be s0. Usually the reason we do this is if you notice in this case behind, my start variable was on the right. And usually you don't want that to happen because it might lead to certain loops while you're trying to convert or stuff like that. So usually just to be safe, we say, okay, I'll make a new start variable. It's on the left and it goes to my old one. Now, to make it easier for today, the examples won't need step 0, so we'll only focus on the other 4 steps. Okay, so step 1, get rid of all epsilon productions. So we have to find the variables that are nullable. What does that mean? It means the variables that at some point will go to epsilon. Once we find these, we have to find all the productions where they exist. And for each one, we'll find what are the possible outcomes if it was epsilon. So easiest way to translate what I'm saying is by seeing it live. So imagine we have this. P goes to A, X, B. So x is a constant in this case, and a and b are your variables. And it's given that both a and b are nullable. So you have to now add new rules, and you'll just say, oh, what happens if a is nullable? Well, if a is nullable, you'll get this rule. B now goes to xb. It's like, oh, imagine a is not there. Or what if b is not there? Well, you'll get ax. What if both a and b are null? Well, you'll just get x. So do you see what I'm doing? You're adding the rules where your variables might be null. But be careful, we're not removing this rule. This rule is still going to be there. We're simply adding these new rules to them. What rule does get deleted? The rule that says A and B are nullable, those are the ones that go away. So if you have A going to epsilon and B going to epsilon, these are the rules that you'll delete, and you're adding these new ones. So that's step one. If at any point there's a step that you don't get, do stop me and we'll go back to it. Step 2, get rid of all variable unit productions. What is a unit production? It's where the right-hand side is only one symbol. So an example would be A could be going to small a, or A could be going to B. Now the first one is okay, because again, what is Chomsky's normal form? I either have a terminal on the right or I have two variables concatenated. But this is not okay. So this unit production, where it's a variable on the right, that's not okay. Simply the way to fix that, so here, as we have A goes to B, to fix that, wherever B goes to, replace it with. So A goes to B. Say B goes to, I don't know, A, goes to C, goes to, I don't know, X, Y, etc. Just replace this B with whatever these rules are to get rid of it. Okay, you keep doing that until you're done with all the unit productions. Step 3, replacing long productions with shorter ones, pretty straightforward. A is going to B, C, D. But that's, again, not okay, because at most it should go to two variables. Just replace. Yeah. We'll make a new variable. E goes to, for example, CD. And replace the CD here with E. So now these both new rules are fine. They're both made up of this binary production that we're kind of doing. Okay, now this is one option. You could have made maybe a different variable that goes to BC and you replace that instead. That's okay. Like there's no, it doesn't have to be just the right-hand side of these 3 digits. It could have been BC. Right, last one. For every terminal on the right of a non-unit production. What does that mean? The unit production, such as this, is fine. Keep those. But in case you have something like this, where A goes to something, but that something has a terminal next to it, we don't want that. Add a new variable like B goes to small b, and we'd replace this B with it. Okay. And we'll get the Chomsky normal form. If you have a question on the rules, let me know. Otherwise, let's just do it. So let's see it in action. That's the best way to get it. Okay, so step 1, I wanna do this. Get rid of all epsilon transitions. So what are the rules? What are the variables that are nullable? Well, S goes to this stuff, so there's no nullable here. X goes to this rule or epsilon. So okay, X is nullable. So I have to here add what are all the possibilities that could happen when X is epsilon. But there are two different x's, and they don't have to be the same x, these two, yes? Like this x at some point might be replaced with this x might be replaced with this, etc. Okay, so I'll ask myself, okay, what happens when the first x is nullable? I'm really left with A, B, or X. So that's one scenario. The other scenario, if the other X is nullable, so we'll be left with this, or both could be nullable, so they both go away. Question, is there another variable here that's nullable, or is it only X? So S is not nullable, X is. Is Y also nullable or not?
Sir, assuming that that
Yeah,
x goes to epsilon and y goes to either x or c, then y is also nullable.
yeah, exactly. And I think Jad agrees with you. Y goes to X. And this is like the second step, right? Where we have to replace this X by everything that that X goes to. But that kind of means, oh, Y goes to X. So an X goes to epsilon. So it's as if there's a rule that says X is also nullable. Sorry, Y is also nullable. Exactly. So we'll have to add all the rules where Y is nullable as well. Jad, as in you can go directly from Y to epsilon. Exactly. You can go from Y to X and X can go to epsilon, so that means Y goes to epsilon too. Okay, well, where do I have my Ys? They're all here. So we'll add them too. So it just means this Y could be epsilon or this Y could be epsilon. So I have to add the rules A or B, right? And once we do that, we added all the possibilities where our nullable variables might be null. So we can simply now get rid of this epsilon. And this is step 1. Okay, now let's do the other step, which is this. Get rid of all variable unit productions. I only really have one. Y goes to X, we just mentioned it. So simply, whatever X goes to, Y is gonna go there too. So I simply removed the X and I just copied all of these here. That's it. If you didn't get that part, let me know. Okay, otherwise, we'll do the fourth. Can I repeat, Jad? Sure. Okay, so here, before, it was like that. Y goes to X. This is not okay. Why? All my rules have to be of this format. Either A goes to either your variable on the left goes to two variables or it goes to a constant. So the second rule actually tells me this is not okay. A going to B is not okay. So what you do is whatever X goes to, the rules, I mean, like X goes to AY, X goes to BY, all of these have to be replaced here. So essentially what I did was the following. Okay, I have AY or BY or A or B. So we added all the rules that X goes to over here. Then once that is done, we can remove this rule where it says Y goes to X. Okay, great. No problem. So now we want to do step 3, which is replace long productions by shorter ones. Now, actually, we could do here two things in one go. We could do two things in one go. I could do step 3 and step 4 together. Why is that? Because basically now, step 3 is saying if you have long productions, replace them with shorter ones. And we do have that here. Like this is a really long production, AX, BX. And step 4 is saying if you have something like A goes to small b, C, replace the B by a big one. And we also have that here as well. So it's like these two rules together, it's okay to kind of maybe do them at the same time or do them like simultaneously. So Majid, you just joined in. We're just doing now the Chomsky normal form. We're going to solve another exercise soon on it, so we'll replace the steps. Just try to keep up with us right now. All right. So let's do them like kind of together. Like step one, maybe get rid of these A's and B's, right? Like I'll add a new rule, call it A, goes to small a, and maybe B goes to small b. Now all I'll do, I'll just replace the A's and B's with these productions, or with these variables. So A here, A here, A here, and even here, like this A, B, it's not okay because it's two variables, it's not just one. So we'll replace here this one with an A too. Keep going with the B's as well. And same thing for these ones. Let me know if this part is okay. So technically now I'm doing the fourth step, move terminals to unit productions. Okay, so now like it's all made up of variables. That's okay. I could have done step 3 first instead of step 4. Personally, I prefer to do step 4 first because now step 3 is a lot quicker. So step 3, long productions must be now shorter. Any hint or any suggestion on how I could do that? So this is a long production.
Yeah,
Mm-hmm.
so for example, we replace a replace a x b, sorry, replace x x b x, let's say, with c.
Okay.
So c goes to x b x,
So
and then
some new variable like c, and you're saying c should go to xbx. Is that what you're saying?
right, and then in the x b x part, let's say bx d goes to bx.
Uh-huh. Okay, I agree with you, Muhammad. That would lead me to the solution, but we can make it a bit easier. Instead of saying C goes to XBX, because this is also going to be a long production, and for it, we're going to have to do something like you're saying is, oh, I now have to make D that goes to BX. Why not make C go to the first part of this, like make C go to AX, and make D go to the rest of it, make D go to BX, and that way, when I replace C here, and I replace D here, you see what we kind of did, right? So now this rule became okay, and this rule is okay, and this rule is okay. Whereas before, if I had left this as xbx, I would have gotten xc, ac. It would have made this rule fine, but this rule would have been a problem. Okay. And actually, these two are enough now to do everything. So this this bx can be replaced with the d, and this ax can be replaced with the c, and kind of everything's okay now. Jad, can I make d goes to bx or b? Now, so Jad is asked here or b. So you want me to add the or b. Question, why the or b? Is there a reason for this? Oh, well, like was there here something? Was there here something and you wanted to replace the b with it? Oh. Mm. There's two things I don't like about that. CB was AXB. Yeah, exactly. So there's two things I don't like about this. First of all is, now this is another problem, yes? Like you're going to have to replace this with all the rules of P. So at some point, this is basically going to be the small b, right? Because like we're backtracking back to step 2. Usually when you go down through the steps, you don't want to go backwards. So we don't want to introduce unit productions, right? So there's this I should have mentioned. Don't create unit productions of variable unit productions, right? So that's one issue. The other issue, I'm not sure if this will actually mess up our grammar when we make a variable go to do different things. Like the reason when you introduced C goes to AX, the reason this is fine, because before, instead of this C, I had AX. Now all I'm saying is S goes to C and C can go to AX. That's all I'm saying. It's still the same like end result. I just added an extra step, so it's Chomsky normal form. But when I add these two rules like or B or something, then your rule, or let me add it for the C, for example, like or B. So for this rule, instead it was AX, but now with the C, it could have been, it can now either go to this or this, which kind of changes my grammar. So two things. We don't want to go back to step 2, and we don't want our grammar to get messed up. Okay, exactly. It might be unsafe. And actually, technically, we're now done with this grammar. It's now Chomsky normal form. We're done. Marwan, can we do y goes to x or c? So you want to add here or x? Like, we already had that
I
rule.
realized X is a subset of Y, so we could just put it.
Oh, so yeah, we could do that, but then it's no longer Chomsky normal form, right? Like actually, if you remember here from step 2, this was all X or C, which is what you're saying. It was X or C, but we change it to this to make it Chomsky normal form, right? So we actually did that using step 2, right? Okay, let's now just make sure, if you have a remark, let me know. Otherwise, let's just do this real quick again for this part. So you can help me with it. Step 1, wherever there's a nullable, we have to see all the possibilities. So S goes to A is nullable, but S is not nullable. Why? Because even if you replace the A's with null, you're still left with something. So S is not nullable, that's good. So or, what are the possibilities that I can get here if A is nullable?
BA or AB
Okay,
or
so
B.
BA or BA or B. Exactly,
No, BA
exactly.
or AB.
Oh, I wrote it twice the same. Yeah, I'll fix that. So it's here or here. So either this A goes away, or this A goes away, or both of them go away. So that's step 1. You find your nullable variables and you just replace all the rules. Why? Because we're trying to get rid of this rule. There's no A goes to epsilon. There's no variable going to epsilon in Chomsky normal form. So we're trying to get rid of that. I also have the A here, so this will just add or small a. And now we can remove this epsilon. So this is step 1. We got rid of all the nullables. Step 2. Now, does actually step 2 exist? Step 2 says, get rid of all variable unit productions. So if I have something like A going to B, I have to get rid of that. And there's none of that here. So I don't have like one variable going to other, and that's fine. So step 2 is okay. We can simply skip it. All right, great. So now we're back to step 3 and 4, which we can kind of do together at the same time. What should I do? So the long ones, we want to make them shorter, which in this case, we only have this is a long one. And stuff like this, I don't want a terminal here. It has to be a variable. So think we can fix it by maybe adding, I think we'll need 2 or 3 rules. What are they?
Capital B goes to small b.
We'll definitely need that. Do we need the capital A goes to
No,
small a?
we already have it.
We already have it. So that won't work. But this A is not okay, right? We have to replace it by something. What should we replace it with? Right? So, okay, so
Can you
this
say
B,
double A?
again, this is specifically the small a. If we replace it with double A, this now can be replaced by either AA again or the small a. So it's kind of
Oh,
changing our grammar. Just be safe, make another variable. Hey, call it C. C will go to A. It doesn't have to be like the capital going to the lower, right? These are all just variables. We
yeah.
can name them whatever we want. So this goes to A. Now I'll replace them. I want to be here and here and here. And the C can go here. What about the last rule that we can have? This is not okay, right? Like, so now this part is up to you. You'll either replace this AB, have a variable go to that, or the BA, you can have a variable going to that. Both are fine. I'll say D goes to, say AB. Okay, so we have D here, and we're kind of okay. If you have a question on Chomsky normal form, you can let me know now. It's really just these steps we go through. And remember, there's always the step 0. Marwan, what about AB in S? That's fine. This I have an AB here. That's completely okay. If you're suggesting maybe I should replace D with here, that's not okay because if I do this, I'm going now back to step 2, right? Step 2, which says I should not have a variable going to a single variable. So unit production variable unit productions, I should not have those. That's completely okay. I could have D here and D here. No problem. Okay. Exactly. All right, so this is how Chomsky normal form usually is. Now, how might this come in an exam? Just try to be comfortable with all the steps. So as I was saying, remember there's also step 0 of making a new start variable. So you might get something like, hey, list for me the steps, or maybe you'll get a certain attempt to convert a grammar, but one of the steps is wrong, or one of the steps is missing. So you have to point that out, right? As long as you're comfortable or you generally understand how the whole thing works, the process, you should be fine. Okay. If there are no questions on Chomsky normal form, we can now move on to GNFA. So it's not really actually, it's not a hard recitation today. It's just steps, it's instructions, right? It's similar to converting NFA to DFA. It's just a series of steps. If you follow them carefully, you should be fine. Now here in GNFA, the steps that we're going to take are to convert into a regular expression. So GNFA, which stands for Generalized Non-Deterministic Finite Automata, the end goal of it is to try to come up with the regular expression of either an NFA or even if it's a DFA, you can do that as well. So say we have this automata. So it's, I think it's a DFA, but and again, it doesn't matter if it's a DFA or it's an NFA, both are okay. What we'll do is, first step, make a new start variable. So start, I'll just call it new start for now. Make a new start variable and have that go to your old start using an epsilon. Again, with step 1, for your final states or for your accepting states, have them go from an epsilon to, again, a new start, or a new end, we'll call it end state, and that state will be accepted. Now, if you had more than one accepting state, like for some reason, say 2 is also accepting, you'd have an epsilon going from 2 to here as well. So you can see kind of why it's generalized, right? Like you're trying to make a new start going to the start. And like all your final states, you're trying to make them go to just one final accepting state. Okay. Assuming we have this, let's just go through the steps to convert it. So step one, let me just rewrite it. Might take a second. Okay, so I'll just name it state 0. It goes from epsilon to state 1. We have 2, 3, and 4. 4 is going to be like your new accepting, and we have an epsilon going here. Okay. So AB from 1 to 2. 2 loops on itself on A and goes B to 3 and comes back. And this here. Hopefully I didn't miss any transitions. Okay, so now this is a GNFA. Technically, this is a GNFA, right? Because you have a new start and you have a new end, and all your end states, in this case, it's just one, but all your end states, they go to this new end one. Okay, so now how can we turn it into a regular expression? We have to, step by step, remove all the internal states. So the internal states are 1, 2, 3. Like all the states from your old DFA or NFA, you have to remove them one by one. Now, how you should remove them, in the end, it doesn't matter. I could remove them 2, 3, 1, or 3, 2, 1, or I'm going to remove them 1, 2, 3 just sequentially. But I might get a different regular expression depending on how I remove them, but it's fine. Like you could have different regular expressions that are equivalent. So removing, say, the first state. So I like to just put the state 1 as your middle state and see all the transitions that go through them. So I have the transition 0, goes to 1, goes to 2. Do you understand what I meant? Just put 1 as like the middle state and see what are all the possible transitions that are passing through it. So I have 0 going to 1 and then 1 going to 2 on A or B. Also have another one. We also have 3 goes to 1 and then goes again to 2. So 3 goes to 1 on A. I'm just reading the graph. 3 goes to 1 on A, and then 1 goes to 2 on A or B. So essentially what this means, if I remove 1, these are my current transitions, but if I remove 1, I'm going to get the following new transitions. I'm going to get the transition that goes now from 0 to 2, and the transition that goes from 3 to 2. So let's see how those look like. So my start, 0. Okay, so 1 is gone. I'm just going to go draw 2, 3, and 4. Epsilon. Okay. Now, what will my new transitions be? You just have to concatenate. Roughly, you just have to concatenate. Like, okay, epsilon concatenated with A or B. That means if I want to go from 0 to 2, exactly as Marwan is saying, it's just simply A or B. What's my other transition? If I want to go from 3 to 2, it's A concatenated with A or B. So if 3 wants to go to 2, it's A concatenated with A or B. However, be very careful that 3 to 2, we already have a transition called B. There is already a transition from 3 to 2. We're simply adding now a new one, so no problem. The new one says A concatenated with A or B. The old one was just B, so we'll say B or all of this. Okay, so I can go from 3 to 2, either just saying B alone, which is my old transition, or this new one that's A concatenated with A or B. Okay, so these are the new transitions. I'll just add the old ones. Sure. Okay. Again, we're moving sequentially. We'll just now remove the other one. If you had any issue with removing one, let me know now. So removing 2, same thing. Let's do this trick where put 2 as the middleman and see all the transitions. So I have 0, 2, and 3. So 0 to 2 is A or B. 2 to 3 is just B. And I have 3 to 3, so this is important. I have 3 going to 2, then going back to 3. This is also a transition. So 3 goes to 2, goes back to 3. And actually, if you really dissect this other transition, once we get rid of 2, it's like we're adding a self loop on 3 to whatever that is. Okay, so 3 goes to 2 on this. I'm just gonna, so I don't have to, so I don't get really stuck on the space, I'll rename this to E1. So all of this is now equivalent to just E1. So 3 goes to 2 on E1. And 2 goes to 3 on B. Okay, cool. However, there's something extra, right? 2 has a self loop on it. So 2 actually loops on itself on A. So what can we do with that? Well, we have to take it into consideration. So here there's a loop on itself on A. There's a loop on itself on A. Any idea what will be the transition when I want to go from 0 to 3? Again, we're removing 2 here. What will be that transition?
A star.
I'm gonna have A star somewhere, exactly, but like the whole thing, was it gonna be? Just concatenate them. So A or B, here, A or B, concatenated with A star. Why? Like, okay, I'm from 0 to 2, that's A or B. While you're at 2, you can like keep looping as much as you want, so that's A star, then followed by B. Okay. Again, the way that it looks from here, the old graph, 0 to 2, that's A or B, then loop A, so that's A star, then a B when I want to go here. Exactly. So that's A or B followed. The brackets are really important, right? So it's A or B, then A star, followed by B. Let me move the star a bit because it looks like it's over the bracket. Any problem with this?
So do we still have to do the union E1 A star B?
That's another transition. So now I have a transition that's going from 3 to 3. So here we have a self loop. And what is that? It's
Oh,
E1
okay.
concatenated with A star concatenated with B. Exactly. This time I'll write E1 as it is. So it's B or A concatenated with A or B. All of that is concatenated with A star. So between these two brackets, I wrote E1. It's all concatenated with A star, then concatenated with B. Right? But is that enough? Yeah, I think that's okay. So we have 0 to 3, that's this transition, and we have 3, 2, back to 3, that's this new transition. Okay, I think now we can do this last one. Remove 3, there's nothing else. So again, we have to keep removing until we're done with all the inner transitions. So S, 0, and now we go to 4, and this is really just the last one. And I only have like one transition. Exactly, Marwan, I want to concatenate everything. So 0 to 3 to 4, in 3, and 0 to 3 we have this, which is A or B. A star B. Here there's an epsilon, and 3 is looping on itself on, I'll call it E2. But very important, E2 is looping, right? So tell me what should I write? Okay, I'll write the first part. 0 to 3 should be easy enough. So it's A or B, followed by A star B. But what about E2?
We also use a clean star.
Exactly, and Marwan's saying the same thing. It's like all of E2 star. So like I'll write a big bracket and I'll put everything, put E2 inside. It's B or A concatenated with A or B, A star, then B. All of this is star. Okay, cool. So like this is the regular expression that the GNFA gets us. So very important question from Marwan. Does the order matter? No. So as I mentioned at the beginning, I could have removed it 3, 2, 1, 2, 3, 1, whatever you want. Hopefully you'd like try to maybe with practice, maybe there's a certain order that's easier to remove. I'm not really sure. Usually I just like to go in uh, incremental order, like I keep going from left to right. The look of it might be different. Like if you had removed it 3 to 1, the expression might have been different, but it would have been equivalent, right? So what I'm saying is the order in which you remove states is not important. You might end up with a different looking expression, but it will be equivalent, right? Like for example, A or B is equivalent to B or A. So this is maybe a very silly or simple regular expression to compare, but these are two different regular expressions, but they're both the same. They're both getting you either A or B. So even if it looks, now it's not gonna be just that looking different, like you might get a really different expression, but they will be equivalent. Okay. Does the order of removing internal states matter? We want to remove the internal ones, right? We don't want to remove like the 0 or the 4. Those are my end and start. Okay. Now for here, I'll leave those for you to practice on. I'll remove one state from here, like kind of to get you to get the ball rolling. Then you can practice it yourself on your own. So here, it kind of looks different because we have an epsilon, right? Like I have an epsilon transition. Does that really make it different though? So we'll make a 0, go to here, and then epsilon here. Question, is this epsilon bothersome in any way? So this is technically an NFA since we have an epsilon. But is it bad that we have an epsilon here? It's fine, it's just like a transition, right? Like remember how we concatenated 0, 1, 2, right? And like 0 here has an epsilon. It's the same thing, it's just an epsilon transition. Like actually, let's just remove 2. Exactly, Marwan is saying it goes away when you concatenate, exactly. So I'll remove 2 here to prove two things, that the epsilon is not scary, and to show you that it doesn't matter the order that you start with. You'll get something. You'll get the right answer eventually. Or a right answer because there's no unique right answer. Okay, so removing 2. I have 1 going to 2, going to 3, and 3 goes to 2, goes back to 3. So there's a loop there. A or B here, and an A here, and we have an epsilon here. So again, the epsilon is nothing. It's just like this is 3 is gonna go to 3, looping on itself with A. That's just it. Okay, so 0 here. Now 1 is gonna go to 3 on what? 1 goes to 3 by concatenating A or B with A. Okay. 3 loops on itself simply with A. Like I don't have 2 looping on itself, so there's no star. It's just 3 looping on itself on A. Now I'll add the missing transitions. I think we only have 3 going back to 1 on either A or B. If I'm missing anything, let me know. I think that's kind of it. And like you can now keep going with the rest. Like now you can either remove 1 then remove 3 or 3 then 1. So you can continue it yourself. However, so continue with this yourself. Remove 1 then 3, for example, but then try again. Okay. So here we removed 2, then you can remove 1 or 3, for example. Solve it, get the regular expression. Try another solution where you remove 1, 2, 3, 3, then, and compare the regular expressions from both solutions. Do you understand what I'm trying to say here? So you'll continue the solution where, okay, right now we remove 2, remove 3, then remove 1. So this solution is 3 to 1. Then you'll do your own solution where you remove 1 to 3, you'll compare the rejects. Maybe they'll be the same, maybe they won't be. But if they're not the same, they're definitely equivalent at some point. Like maybe if you try to expand them, you'll get something similar. Okay. And here is just another example. This one maybe is a bit longer, like if you really want to test yourself. But an important question here, you can maybe ask yourself, what if Q3 or some other state other than Q5 was an accepting state as well? It doesn't have to be specifically U3, but I want you to know that it doesn't just have to be one state, it could be more than one state that is accepting. In that case, you simply, okay, Q0 is your new start. And your new ending, or your new accepting, I keep saying ending, is going to have an epsilon from here and an epsilon from here. Okay, very important because we didn't see an example on that. When you have 2 or multiple acceptings, you simply add an epsilon all to this to the end state. Again, it's nothing more than simply we're going to get now more or newer transitions. Like now when you're removing Q3, it's not just going to be 2, 3, 4. It's also going to be 2, 3, 6, right? In terms of transitions. Okay. If you have any questions on the GNFAs, now's a time to ask. Again, it's just steps that you do. And I think this hint or this thing we do where when you're removing a state, you try to put it as the middleman and you see all the different transitions that go through it. I think this is really helpful. Okay. So technically, we covered the GNFA and the Chomsky normal form. Now I'm just going to go through a few more ideas on regular expressions or regular languages in general. After I'm done with those, if you want to ask something yourself on a different topic, feel free to do so. Okay, so methods on regular languages. So you remember regular languages, they are what NFAs and DFAs represent. We can prove that a language is not regular by using the pumping lemma, but what other questions could come? What other ways of thinking are there? Well, for example, this. Given that the language L is regular, is L concatenated with L reverse regular? What do you think? I have a language L, it's regular. Is L being concatenated with L reverse regular as well?
Sir, نحن we know that if let's say if we concatenate two languages that are both regular, then the result is regular. So we have to prove that L reverse is regular.
Exactly. So there's no problem with the concatenation. Really, the only thing you need to prove is that is the reverse regular. Now, I'm not sure if it's like given to you in the lectures, like by default, L reverse is regular. It is, but if we want to prove that, there are multiple ways we can do it. First of all, maybe by abstraction in terms of just drawing, right? So L is regular. That means there's some machine M that represents L, right? So this machine accepts the language of L. I'll call it M1. So M1 accepts or defines the language L. Defines. Okay. So what is M1 basically made of? Well, it has a start state. There are a lot of transitions. There are some accepting states at some point, etc. Jad, if you intersect L reverse with another regular language to make L, like we did in okay. So I think Jad is so in the last recitation we had this idea where there is some language that is the so LA intersection with LB with LC. So Jad is saying if LB and LC are regular, then LA it has to be regular. So I think what Jad is saying, if we can make these the intersection of some other two things that are regular, we'll get the answer. I'm not sure if we, so that's a really cool idea. I'm not sure if we can do it here because we're talking in general, like it's not specific languages. And maybe if it was specific languages, like L is the even numbers or something like that, maybe we could have gone through that. But since here we're talking in general, we have to answer it in general as well. Okay, so this is the language L. Really, what is the language L reverse? It's just the reverse of the strings, right? It's just the reverse. So the way that we could do that, think about it like this. You can't really flip the string, right? Like, okay, if you're testing here AAB, and if this automata accepts it, then if there's a machine that represents L reverse, it should accept BAA, which is the reverse. Okay, so we flip the string and we're gonna feed it. But how can we now make use of that? Simply, you can just flip the transitions of the states that you had before. So it's two ideas. You flip the transitions, right? Think of it, it's kind of intuitive. Oh, if I'm going one way, if I flip the transition, it's like now I'm going the other way around. But another thing we also have to do, your start state from the old one is now going to be your accepting. Your accepting from the old one is going to be now your start. But you might tell me I might have multiple accepting. Can I have multiple starts? For the sake of simplicity, we can assume that there's just one accepting state. And even if there isn't, we can do that because go again to GNFA. Just make it a GNFA, right? So now you just have one accepting state. So now that accepting state, instead of it being accepting, it's going to now be a start. So what did I really do? Two steps. The transitions, flip them. The start state, make it now accepting. And all the old acceptings make them now starting. Or like make them all one accepting and one starting. Does that make sense? Any issue here? Mhm. Now, in some places, they might assume that L reverse is regular, but in kind of trying to prove it, this is one way of doing it. Flipping that transitions and then swapping the accepting and starting state. This is if we're trying to do abstraction, which is what we saw in the first recitation. But if we actually want to try to write it, so I want you to try and be comfortable with the definitions, right? So going back to the first chapter of the course, the formal definition of a finite automata. What is really a finite automata? It's made up of Q, which is all your states, your alphabet, sigma. This is the function that gives you all your transitions. So here, when I say, for example, I have maybe state 1 going to state 2, like this transition R2 going to 1 on A, it's all existing here in this function. You have S, which is your start state, and F, which is the set of accepting states. Okay, so when the question is saying, given that L is regular, what that means is you have some machine M1 that gives you all of this. So I'll call this M1. You have your states, you have your epsilon, your sigma, alphabet, etc., and all of that. What we're trying to create now is M2, where, for example, the language of M2 is the reverse of language L1, right? And remember, it's the same states, of course. Like we didn't remove or add any new states. It's the same alphabet. What really changes are these three. So here we had maybe 1, 1, 1. Here it's going to be kind of different. How is it going to be different? Again, the transitions are reversed. So if here you had 1 going to 2 on A as a family of transitions, a function of transitions, here's going to be reversed. Here you're going to have 2 going to 1 on A. So you're kind of flipping these. Now it's like the old state is going to, now again, this is generalized, but you kind of see what I'm trying to say. Like if I had 1 going to 2 on A, now I'm having 2 going to 1 on A. And as we mentioned, the accepting and the final states are flipped. So if we assume this is a function and you're giving the arguments in a specific way, all you have to do is say, oh, F1 and here S1. Do you see what I'm saying? Like, now S1 is my accepting, so the start is now accepting. And the old accepting is now the start. And of course, we can, for simplicity, assume you have 1 accepting. So this is really the almost 90% or 95% formal way of answering the question. Like if the question was just prove that the L reverse is regular, you'd have to go through that. So be comfortable with this language, like what officially a finite automata is and how you can kind of play with it. Did I lose anybody here? Has anybody lost? Okay. If you're lost or you want me to repeat something, let me know. We may have went overboard with this question. I think I need about maybe 5 or 10 minutes, and we'll be finished. If you need to leave, of course, I understand. So, in short, yes, this is a regular language. In short, again, why? L is regular. So L reverse is regular. Why it's regular? Flip the transitions, switch the accepting state with the starting state. And as I think Muhammad said, the concatenation of 2 regular languages is also regular. So this is since maybe this. Okay. What if we get something like this, alternating odd A, odd A, even B, etc., which is again what we solved in the first recitation. So if you're given something like this and you're asked to prove if it's regular or not, now what is a way to prove that it is regular? So yes, it is regular since we
Say that the machine recognizes it.
exactly. First of all, obviously it's regular since we were able to do a DFA for it in the first recitation, and that's the answer. Since you were able to make an automata, a finite automata, which either is an NFA or DFA to represent it, that means it is regular. So you can either do a DFA or an NFA, or you can come up with a regex for it. So if you come up with a regular expression for it, well, the word is right there, regular expression. That means it's a regular language. It was actually one exercise that I I left it for you to try to actually get a regex for this. Okay. Assume you have three languages, L1, L2, and L3. You are given that L1 and L3 and the concatenation of all three languages, all of those are regular. Does that mean L2 is regular? So again, L1 is regular. So maybe you have some machine M1 for it. L3 is regular. So maybe you have some machine M3 for it. The whole concatenation, L1, L2, and L3, that's regular. Does that mean L2 has to be regular too? If you really think about it, this is asking, is the reverse of the closure under concatenation if that is regular? Like, what do we know about the closure as we proved with this? If this is regular and this is regular, that means the concatenation is regular. This is kind of asking the reverse. If the concatenation is regular, and like two of them are regular too, does that mean the whole thing? Does that mean L2 is also regular? Okay. So what we really want to know here is, do I have a machine M2 that represents L2? I'll give you a hint. Intuition-wise, why would I say yes or no? Since I kind of told you, we're saying the reverse of what we did here. If you have two languages that are regular, the concatenation, the intersection, yes, that's going to be regular too. Is the reverse true? Not necessarily. This is similar again to here, LA, etc. It's like they're asking, if this is regular and this is regular, does that mean that this is regular too? Not necessarily. Okay. The way to prove that, we need a counterexample. So we'll just finish this one and we'll end it. So I also have some true or false. We can solve that next week. So this is the last question. I need you to help me with this. So imagine you have some language that is regular. So we'll solve it using a counterexample, not by last time maybe we did contradiction. This time we'll do something called counterexample, where if we can give an example where this fails, then it's not regular. So imagine a regular expression concatenated with an irregular one, concatenated with a regular one, etc. If you can give me an example like this and you get a regular, that means the whole thing. That means this is wrong. How about this one? I'll give you the expression. You just tell me if you agree or not. If I put here A star, and here I'll put B star. So the language of A star, that's definitely regular. The language of B star, that's also regular. What do you think we can put here something that's irregular? Something maybe we've seen a lot? Yeah, exactly. AN, BN. Why is this all regular? Because it's the same thing as A star, B star. I know it kind of looks like we're saying, oh, you have some number of A's, then you have exactly the same number of A and B, then you have some B's. I know when we say it like this, it kind of seems like it's not regular because at some point you're forcing the same number of A with the same number of B. That's what the intuition says, which is true. However, this is equivalent to A star, B star. That's like saying, oh, sigma star, since at some point inside of it I have A and B on, that means sigma star is not regular. That's not necessarily true. Yes, there is A and B on, but the language is much bigger. So for example, I'll try to convince you by doing the following. Remember, I'm trying to prove that A star, A and B on, I'm trying to prove that it's not only regular, but it's also equivalent to A star, B star. Well, what are all the possibilities for n? N could be 1. So that means I have A star, AB, B star. N could be 2. So I have A star, AA, BB, B star, and so on. And like this language is the union of all of these. But one of, like if you union n1 to like infinity, these cause the problems. However, for n0, it's just A star, B star. It's being also unioned. A star, B star, union all of these. It's like A star, B star will eat all of them because they're all subset from A star, B star. It's just any number of A's followed by any number of B's. Let's see what Chad is saying. Since A and Bn can be surrounded by a different number of A's and B's, it doesn't matter the totals if the total string contains a subset A and Bn. Whatever the result you can get with the full expression is also possible with A star, B star. That's exactly what I'm trying to say. So that last statement, whatever you can get from this expression, you can also get it from this one. Give me anything. They're both the same. So even though there's like an n here and an n here, since it's equivalent to this language, I can simply make an NFA for it, and I'll accept anything. Like try to give me any string from this format that you think I can't accept, it'll get accepted here, including just A and B on its own. So it's kind of like, this A star is eating this AN, and this B star is eating this B. Okay. If you have any questions, you can let me know. You didn't get this, we can repeat it. So I'll maybe just try one last attempt in case somebody's not convinced. So A star, AN, EN, B star. This is like this is equivalent to all the possibilities for n, right? So it's like this, let me call this maybe L. It's like L when n is 0, union L when n is 1, union with L when n is 2, etc. Like you can at least agree with me here Like it's all the possibilities when you put here 0, or when you put here 1, when you put here whatever. However, this first one, when n is 0, you simply get A star, B star. And everything here else is subset from this one. Like if you tell me, oh, A star, then AB, then B star. Oh, this is like A plus B plus, right? Well, this is subset here. Then this one will get you at least 2 A's, then followed by at least 2 B's. That's also subset here. They're all subset from that bigger one. So subset here, subset here. It's as if the whole thing is A star, B star. So back to the original question. This was language L1. This was language L3. L1 and L3 are regular. L1 concatenated with L2, concatenated with L2, concatenated with L3, the whole thing is regular too. However, this one is not regular. So by counterexample, it's not right. Yeah, so just by counterexample, we're done. Okay. If you have any questions, let me know now. Otherwise, see you next week. So we covered Chomsky, we covered GNFA. I think we have one more big idea, which is the pumping lemma for CFGs. We'll do that next Tuesday, and with whatever time we have left with the recitation, we'll try to revise. And if you have any questions, make sure you bring them. We'll solve them all on campus. See you next week.